Today, we're going to examine 7 distinct network access control enforcement methods. We will look at how they work, what their infrastructure requirements are, and their documented operational outcomes based on an analysis of thousands of deployments.
So, the choice of an enforcement method has direct consequences. These consequences impact the deployment timeline, the infrastructure investment, and the operational overhead for the system. The information we're covering comes from an analysis of documented outcomes from over 5,000 deployments. These are across sectors that include financial services, government, healthcare, and manufacturing.
Okay, so let's get into the core enforcement challenge identified in these networks. Modern networks contain more than just managed PCs. You'll find IoT devices, operational technology, building controllers, BYOD endpoints, and contractor devices, often on the same infrastructure. The enforcement method has to cover the device population that actually exists.
The IEEE standard for port-based control is 802.1x. In practice, it presents specific operational challenges that have been documented. As Genian NAC notes, 802.1x is costly and requires large-scale network configuration changes, and handling exceptions creates significant management overhead.
These challenges show up as 3 distinct issues. First, there's switch compatibility across different vendors. Second, there's device compatibility, as many IoT, OT, and printer devices do not support the 802.1x standard. And third, using EAP-TLS requires certificate management. Well, these limitations led to the development of alternative enforcement methods. We will now cover 7 of them, one by one.
First up is ARP-based Layer 2 control. Here, a sensor intercepts ARP requests and will either drop or redirect packets from a non-compliant device. This method doesn't require any switch changes and is vendor agnostic. A documented limitation is that a device with a static ARP entry can bypass this control. This can be mitigated by what's called a strict mode or by using an agent.
Method 2 is span-based control. It works by monitoring a copy of network traffic. If it identifies a policy-violating session, it sends a TCP reset or an ICMP unreachable message to terminate that session. The requirement here is a switch capable of port mirroring or a network tap. A limitation is that any traffic not passing through that mirroring port cannot be controlled. Method 3 is port-based network access control using the 802.1x standard. A built-in radius server can assign a device to a quarantine VLAN or force it to re-authenticate using a change of authorization. The requirements for this are 802.1x capable switches and access points, as well as endpoint supplicants. For devices that don't support it, you need to create MAC authentication bypass, or MAB policies. And EAP-TLS requires certificate management. Next, we have DHCP server-based control. A built-in DHCP server will either assign or withhold an IP address based on policy. The requirement is to either replace or integrate with the existing DHCP server. The limitation is that endpoints with a static IP address will bypass this control. Method 5 uses the Simple Network Management Protocol to disable a switch port. It remotely disables the physical port of a non-compliant device. This requires SNMP write access on MIB2 compliant switches. The result is that all traffic on the affected port is terminated. The 6th method is inline packet filtering. A sensor is placed physically inline between network segments. All packets that pass through it are inspected, and non-compliant packets are dropped. The requirements are hardware with 2 or more network interface cards and a high availability configuration for redundancy. This method introduces latency and is a potential single point of failure. And the 7th method is agent-based actions. This involves an agent installed on the endpoint for direct device control. The agent can control the Windows firewall, network interfaces, or block static ARP configuration. This method applies only to the endpoints where the agent is actually installed. Okay, now let's move to a direct comparison of 2 of the most frequently discussed methods, ARP control and 802.1x. We'll look at the operational variables for each. A documented outcome of failed 802.1x only projects is no enforcement at all. An outcome with no enforcement is less secure than having a functioning alternative policy in place. The quote here says, "Many deployment failures occurred because applying access control all at once proved too difficult." This table shows a direct relationship between the security level of a given method and the infrastructure it requires. For example, ARP Layer 2 control is listed here with a medium security level and no infrastructure requirement. On the other end, inline filtering is listed as having a very high security level with an inline hardware placement requirement. Now, for the operational trade-offs. An 802.1x environment requires switch reconfiguration. It also requires MAB exceptions for IoT and OT devices, and it incurs certificate management overhead. In contrast, an ARP-based environment applies to existing infrastructure, covers IoT and OT without exceptions, and has no certificate management overhead. So, this data suggests an enforcement sequence that's based on the realities of the environment, not on initial assumptions. This is referred to as a phased enforcement approach. Here's the documented three-phase path. Phase 1 is visibility. You deploy and monitoring mode to map the entire network. Phase 2 is establishing a baseline of control, for example, by activating ARP-based enforcement for network-wide control without changing infrastructure. Then, Phase 3 is layered enforcement. This is where you apply methods like 802.1x, SNMP, or SPAN, but only to specific segments where the infrastructure and the requirements align. And this leads to the final consideration, the architecture of the NAC platform itself, and the impact of choosing a single method versus a multi-method platform. So if one method hits a constraint in a particular network segment, a multi-method platform can use another method to cover that segment. This allows the project to proceed. As the quote says, all options must be available for selective use. This table illustrates the difference in capital expenditure based on the platform architecture. An 802.x only platform requires switch replacement, an external radius server, and a certificate infrastructure for EAP-TLS. A multi-method platform does not require switch replacement and can include a built-in radius server. It also doesn't require certificate infrastructure for all of its methods. And these are the ongoing operational costs which accumulate over the life cycle of the deployment. For 802.1x environments, these costs include certificate management, dealing with supplicant issues, and maintaining per-device MAB policies. For environments using ARP, SNMP, or SPAN, those specific operational drivers are not applicable. So, the final takeaway is a question of architecture and the direct impact it has on deployment outcomes and total cost. Does the platform adapt to the network, or must the network adapt to the platform?